Today we want to talk about one of our favorite framings in Calc 1. This is essentially an engineering class, and that's position, velocity, acceleration. We know how to find derivatives. We know how to find antiderivatives. We know about definite integrals. We need to see some of these things in a context. So this is a great context for us because it's one that we understand. Position, velocity, acceleration. Now, when I say that we understand this, we intuitively understand this. Y'all intuitively have an understanding of how calculus works. You understand the relationship between position, velocity, acceleration. You make these calculations instantaneously in real time as you're walking around. So you're walking, let's say you're walking one way and another person is walking another way. You see the other person walking and you can tell if you maintain course that y'all are going to walk into each other. And so you can see that in a certain amount of time, your position will be the same and you will bump into each other. And so one of you applies some acceleration and slows down, changes your velocity to slow down. But then the other person also applies deceleration and slows down. So then you realize that you're in the same, going to be in the same position just a little bit later. So the other person speeds up, then you speed up, and eventually you like come face to face, like all, then you make the final adjustment there. But you make adjustments to your acceleration. You apply acceleration or deceleration to change your velocity so that your positions don't match. And you do this just by observing things and seeing how things work. So you have an intuitive understanding of these relationships. We just want to codify that with math. The relationships here, we have position. If we think of position as a function of time, velocity is the rate of change of position with respect to time. Velocity is the rate of change of position with respect to time. This is calculus. I just wrote the words rate of change. I just said derivative without saying derivative. Well, I just like literally just said derivative. Velocity is the rate of change, that is the derivative with respect to time of position with respect to time. Acceleration is how your velocity is changing. So your acceleration is the rate of change which is derivative of velocity with respect to time. Velocity is the derivative of position. Acceleration is the derivative of velocity. That makes acceleration the second derivative of position with respect to time. So if we have a position function, so if S of t is position at time t, then S prime will be the velocity. And S double prime will be acceleration. From a unit standpoint, If we measure position in, say, meters, if x is in seconds, or t is in seconds, and s is in meters, then ds dt will be meters per second. Remember, we make the units of the derivative by making the units of slope. So the units of velocity will be meters per second, and the units of acceleration will be meters per second per, per second, or meters per second squared. Usually simplify that to meters per second squared. That's just simplifying meters per second per second. It makes sense because meters is how s is, the velocity is ds dt. S is measured in meters, t is measured in seconds. So ds dt will be measured in meters per second. Units of the slope, units of the derivative are the units of slope. Same thing happens with acceleration. I wrote meters per second because acceleration is the rate of change of the velocity with respect to time. dv dt. V is measured in meters per second. T is measured in seconds. So dv dt will be meters per second per second. We simplify that to meters per second squared. So we need to make this calculus problem, of course. Well, it's already a calculus problem. I talked about derivatives. But we have both directions of derivative now. We know derivative and we know antiderivative. We know differentiation and integration. So starting from position, we look down the rate of change. This direction is differentiation. Differentiation just means taking derivatives. Since we now have antiderivative technology, we have integration technology. Go in the other direction. We have integration. If you would recall, we considered sign and direction and concavity. We talked about sign and direction and concavity. The sign of the derivative tells you the direction of the function. The direction of the derivative tells you the concavity of the function. The way that we played that game, close enough. The way that we played that game is I gave you a derivative. And for the most part, we've been working on the fundamental theorem of calculus. So I gave you a derivative. And when the derivative was positive, you know that the function is increasing. And the area tells you by how much. So let's suppose that we have a function Let's consider a velocity function. Let's say we have a velocity function and this goes from, let's say, t equals 0. Let's suppose that this happens at t equals 6. And then this happens at t equals 10. This is going to be some velocity function in, let's use meters per second. Seems a little bit big, but that's fine. Let's suppose that this area here let's call that A1. And let's say that area 1 is equal to 20. And let's say down here, this area up to 6. And let's say down here, and it looks like we have less area. So let's say the area down here, call it A2. Let's say that area is equal to 8. We can see, let's read what's going on. Let's read what this velocity graph is telling us, what this velocity function is telling us. So between t equals 0 and t equals 6, we can see that our velocity is taking us one direction, and we do that for 20 meters. And then from 6 seconds to 10 seconds, that's pretty fast. That's fine. And then from 6 seconds to 10 seconds, we're moving in the opposite direction. So whatever direction we were moving from 0 to 6, we're moving in the other direction from 6 to 10. And so our overall change in position will be 20 minus 8, or 12 meters from where we originally started. 20 meters one way, 8 meters the other way. So let's put some more context on this. I'm going to give you the most popular context. This is from looking at lots of AP tests. For those of you who have taken AP tests, might be familiar. Let's consider a velocity function. This is the velocity of a particle moving left and right, or let's say right and left along the x-axis. Let's say that positive velocities move the particle to the right. So in this context, given that we have the area of the graph is in meters per second. So the area is going to be just length times width. I'm going to take those meters per second on the y and multiply by the units seconds on the x, or in this case, t, meters per second times seconds. That gives us meters. So in this context, our area is going to be in meters. These are both going to be in meters. This area is just length times width. In this case, length is meters per second, width is seconds. Meters per second times second is meters. Integration is multiplication, but one of the factors is continuously variable. So if we want applications of integration, it's all the applications of multiplication. Everything that we use multiplication for is a thing that we might have to use integration for. Now we can use this graph to describe what's going on. From t equals 0 to t equals 6, the particle moves 20 meters to the right. From t equals 0 to t equals 6, the particle moves 20 meters to the right. In calculations, this should show up as the definite integral from 0 to 6 of v of t dt. I didn't calculate this. This was given. The particle is 20 meters to the right of where it started. From 6 seconds to 10 seconds, the particle has turned around. The velocity has changed from positive to negative. We have reached a maximum, a local maximum of position, as the velocity is 0. And then from, oops, just write that. From t equals 6 to t equals 10 seconds, the particle moves 8 meters to the left. This would show up in the calculation as the definite integral from 6 to 10 of v of t dt equaling -8. At this point, the particle would be 12 meters to the right of where it started. If I look at the definite integral from 0 to 10, that definite integral would be 12. Because we'd have the 20 from the integral from 0 to 6, and the -8 from the integral from 6 to 10. So the definite integral from 0 to 10 will just be the sum of all the other integrals. It moves 20 meters to the left, sorry, 20 meters to the right, and then 8 meters back to the left. That's positive 12. After 10 seconds, the particle is 12 meters to the right of where it started. At this point, we want to clarify what we mean with that, what we mean by position. Position is different than distance, and distance is different than displacement. Velocity is speed with direction. Velocity is speed with direction. In your car, you have a speedometer. It tells you how fast you're going regardless of the direction. The speedometer told me I was going, I'm recording this, 50 miles per hour on the way to Skyline, and it will record a speed of 50 miles per hour on the way back from Skyline. It might be higher, but let's just go with 50 because that's the speed limit on 35 out there. It doesn't say it's positive 50 in one direction and negative 50 in the other. So in this problem, in this case, the 12 indicates, since it uses positive and negative velocity, since it has movement to the right and movement to the left, we would say that the 12 represents the displacement of the particle, how much it is displaced from its starting position. So the 12 for t equals 0 to t equals 10 seconds, the displacement of the particle is 12 meters. The displacement of the particle is 12 meters. The distance that the particle traveled is 28 meters, 20 to the right, 8 to the left. Distance that the particle traveled is 28 meters, 20 to the right, 8 to the left. Distance is your odometer reading. Displacement is how far from the starting point. This is why we can't have speedometers with direction on it. Otherwise, you just drive the car back to the dealer and say, oh, how many miles have you got on it? And you'd be like, oh, 0, because this is where I bought it. Displacement cares about the sign, positives and negatives, and distance is like the absolute value of all the things. Any questions? Some of the things that we've seen before, we see the derivative as 0 at t equals 6, and the function is changing, the position is changing from positive to negative. So we have a local maximum at t equals 6, a local maximum of 20 at t equals 6. So some other things to observe. And no space to observe them. Let's say that the position function we see a local maximum of 20 at t equals 6. Twenty is the maximum distance from the starting point. And since this is the farthest that we ended up from the starting point, this is also a global maximum on the interval from 0 to 10. Looking at some other things, features on the graph. At one point, our velocity is increasing, and then our velocity begins to decrease. And that happens about right here. At approximately t equals 2 seconds, close enough. Actually more like halfway. Let's call it 3. At approximately t equals 3 seconds, the velocity changes from increasing to decreasing. So our acceleration goes for we have positive acceleration, and then at 3 seconds, we have negative acceleration. So the position has a local maximum of 20 meters at 6 seconds. The position has an inflection point at 6. The velocity has changed from positive to from increasing to decreasing. So the position changes from concave up to concave down. So this is the game we want to play this week. Position, velocity, acceleration. Velocity is the derivative of position with respect to time. Acceleration is the rate of change of velocity with respect to time. We're just applying that to thinking about sign of the derivative tells us direction of the function. Direction of the derivative tells us about the concavity of the function. Any questions? Comments? Any thoughts? We'll practice a problem like this tomorrow. All right, that's going to do it for today. Welcome back. I hope y'all had a nice spring break. There's a sign-in sheet somewhere. Make sure you sign in on the sign-in sheet. Everybody have a good day, and thanks for playing.